Okay, so good afternoon. So I'm just going to do a few slides first before I get into a long demo. So I'm going to talk about live programming. This is a term that has many different meanings, but I'm going to talk about the specific meaning that I'm going to use here. So programming has been an evolution of getting more and more interactivity. So we started off with, back at the beginning, we had cables. Then we had punch cards and teletypes, and finally we get terminals and stuff, right? And then today we have multi-monitor setups, but programming is still sort of like a. But where we really want to go is we want to go to what's the future like? How is programming going to become more interactive, right? And we kind of see a hint of this in movies and these fake user interfaces. But will we ever be able to realize those? Today, programming is really like archery. You aim your arrow, that's your editing. You let your arrow go, you're debugging, and you see where it lands, and then you start again. And every time you do that, you edit, you debug, and then you edit again, and you debug again. It's not a very continuous experience, so there's a lot of discontinuity there. And what we really want is water hosing. So there's an Olympic sport for archery. There's not an Olympic sport for hitting targets with a water hose because it's really easy. You just move your water hose over and you hit your target, right? And I think this is the kind of experience that we want for programming, if we can achieve it. And I think that really goes a long way for us to realize sort of the next generation of programming interfaces. Okay, so we're going to improve the feedback loop between the programmer and the computer. And I'm going to do a demo here. There's a lot of things that some of you might have seen before. I think I've stolen ideas from a lot of really great people. Chris Hancock in his live programming dissertation is one of my big influences. And then Brett Victor, of course, describing calculator and learnable programming. I mean, there's not a direct connection to live programming there, but I think the connection is natural and obvious. And Alexander Rapini in his conversational programming work. So I'm just going to start with a demo and just continue on with it. Let's see, what's my old key here? Okay, good. All right, and I don't want to see that. Go away. All right, good. I'm trying to get Windows to hide the taskbar is impossible. All right, so I'm going to I'm going to sit down here because I'm going to do a lot of typing. So I'm going to start off with a question mark. And I know in Chris Granger's talk, he was using the question mark for something a bit different. But here it means a hole, something unknown. And it applies real estate to that, syntactic real estate to that concept. We can probe it, and we can see that it's a void type, because all statements are void type. And we can actually perform code-completion on this. So I'm going to code-complete. We don't have a lot of void methods right now, but we have draw, insert into a set, insert a lot of items into a set, log, put from a dictionary, and so I'm going to choose draw. Now I'm going to hit return here, and we now are drawing something on the screen, right? And we have more, I call these holy terms, right, with an E, so it's not religious. But we have all these holy terms here. One is, what are we drawing? Some random geometry. The color of what we're drawing, green, and then pen and z-index, which is we're not using. So these holy terms have default or random values depending on the context. So as soon as I code-complete on draw, I get a bunch of holy terms. They have values, and something is drawn on the screen over here. Right? We don't have to wait. Right? I can code-complete on this holy term again, and we get circle, condition, hexagon, pentagon, and we get a lot of other choices that might make sense in certain contexts but are not entirely high priority. Right, so let's pick a hexagon. Okay, so now we get a hexagon on the screen. Okay, and we can fill in the position here. 10, 100 by 100. Let me make this. Give us a little bit more space on the code side. I can take that. I'll take that way if I need it. And then we can give it a size 100. Ooh, Give me my keyboard back. 100 and maybe a color would be nice here. We'll just do co-completion there. Blue. OK. So I made a bunch of discrete modifications here. Well, let's just do it like this. OK, I made a bunch of discrete modifications here. But it's not really continuous, right? I mean, you know, if I'm editing my code, right, and I have to type, you know, if I want to go from 100 to 200, I have to delete the 1 and type a 2. The same here, right? And that's not very nice, right? I mean, it's, yeah, OK, you get to see the result right away, but this hexagon is just jumping all over the place, right? So let's, you know, do something called scrubbing. So I mean, scrubbing is this concept. I think it's from audio-visual field, but I think Brett Victor kind of defined it in the computer field where, you know, you're editing values via continuous input. So we're going to take 200. We're going to go back to 100 here. And, OK, 102, fine. I don't know how to use the mouse. Sometimes it depends on how nervous I am. All right. Well, whatever, close enough. Right? But the thing is that as we do this scrubbing, we can see, you know, it moves continuously. We can eye it, right? We have a water hose. Before we didn't have a water hose. Before we had a very fancy bow and arrow, and now we have a water hose for real. OK? But we can also scrub, let's say, on the entire tuple, right? So now we're just moving it around, you know, via 2D input. And this is possible because the type of this tuple is position. So we're using type inference. It's going to the tuple and saying, hey, you're really a position. And that's being used by the scrubbing system to say, OK, well, we know how to scrub position with this 2D widget. So type systems, static types are actually useful. But you do not see any static types here because we have inference. And that's why inference is useful, right? We can do the same thing with, you know, the size. And again, it's a length 1, and it knows how to scrub that. It's not just a number, right? The size is actually limited to the size of the related to the size of the screen. And we can also scrub colors, right? I'm going to click here, and we get a bunch of colors, and we can scrub that, right? So OK, maybe crimson is a nice color for this hexagon. We can do more than that, right? We can kill this and make it a tuple. Because, you know, color is just a 3-dimensional thing, right? And we can look at this tuple. It's going to be a color, right? And we can actually see, well, maybe there's a custom scrubbing widget for that, right? And now we can choose a nice, custom color for it, as opposed to a literal color that's preset. OK. And finally, we have shape. We can scrub shape, right? We can make it a pentagon, triangle, rectangle. Let me stop there, and let's go up. Square, circle. OK? So we can scrub that. And it's quite useful, right? Deciding what you're going to do, scrub a shape. OK, so let me go and load up some boilerplate code here. I don't want the Windows icon. OK, so now I've reset the simulation, and I've reset the code. Man, that's horrible. Let's see if I can make that a little bit nicer. OK. Just give it more space. OK, now I'm going to make a bouncy ball, right? So we're going to set the position to be p. P is up here. It's a variable assigned to a holy term. As soon as we assign p, right, here it's just any. It doesn't have any meaning. Let's see. Show it to me, any. OK? But as soon as I type it here, right, this holy term is now a position, and it has a value. Because positions have default random values as their default, as their evaluation in a holy thing, right? And then we can set the diameter of the circle to be d, and it's given a value when we make that. And let's center it, because now position is the left top position. We want it to be the center so we can do physics calculations on it. So let's subtract that, right? Now we get this nice. Now the position is here. And we're going to move that out. And then create this term called RR. It's going to be initialized to a holy term. And I'm just going to drag that here and move that code up. OK? Now, I should mention here that this is a programming language. It's imperative. It's not declarative. It's not data flow. It's not functional. It's imperative, but it has React-like features. So now I'm going to do this on tick here, which is on every tick, time tick, and I'm going to do something with the position. I'm just going to add the velocity. There's this V. I'm sorry, I'm pointing at my screen. There's a V up there, here, that we can actually use to do something with that. Now what happens is that once I've done that, right, there's a strobe here that does 200 frames, and it samples it every 10 frames. So it's executing it up to 200 frames, and then every 10 frames or so, it's being sampled, right? But we can control where we see the ball in time by scrubbing on tick, right? This is not changing the tick event. This is scrubbing what tick event we're visualizing. And tick event goes off every frame, so every 15 milliseconds or so. Okay, so we can scrub that, and we can actually see where the ball is. And we're going to do the same for velocity. Now we have a falling ball. And of course, we don't want that ball to fall off the screen, so let's go ahead and clamp it. But to do that, I'm going to have to create a new position here. Holy term again. I'm going to move this up. Okay, what am I doing wrong here? I'm going to clamp it. Co-completion, clamp is right there. Co-completion again. Let's look for the minimum. Okay, RR which is the size of the radius of the circle. And then we just need the screen size. Now we see the ball. Oh, well, it's kind of clamped, but not really. It's falling to the bottom of the screen, so we need to subtract RR from here. Okay, now it's there. Now it's up. Okay, and we need to do something else with the velocity to make it bounce off the screen. So we're going to multiply that by this inflect command down here. Let's see, P1 and RR. Now it's a bouncing ball. Okay. So now the inflect one is defined down here. It's just a user-defined function that does something based on the screen size. Let me make that smaller. This is good enough. Okay. I keep running out of screen real estate here when I cranked up the font. Okay. Now I'm going to create an abstraction. So we're going to define this thing called ball. And its body is just going to be a holy term. And I'm going to drag the holy term down to this plus and move that all up. And since ball is not being called, it just disappears, right? Because we're no longer drawing a ball. We just created a method that draws a ball. And we're going to define a for loop here. I in 0 until 2. And then we're just going to call ball. Okay, actually use co-completion for that. There it is, and we get 2 balls. Okay. So now if I drag that again, you can, ooh, that's because I'm running out of space. But if I scroll down, I can actually do it. Okay. Okay. Now, we're going to debug this, or we're going to at least inspect it, right? So I'm going to do this control. I'm going to select the ball, and I'm going to do Control G. And I just typed Control G, and I went down 2 lines to the ball definition. And I just didn't navigate to the ball definition. I set the execution context, the debug execution context of the ball method to the ball that was being executed on this line, right? Now if I probe, I can probe any value here, and I can see the color. So this is the purple one. Sorry, pointing at the screen again. I've got to get out of that habit. The purple one, the lower ball, the one that's purple and the other one's kind of red, right? And now I can actually make that stick there. So I can put a little @ symbol here and make that stick as meta text in the program. And I can probe other things here. I can probe the position, for example, and the velocity and whatever. But there's more. There's 2 balls here. Actually, there might be more than that. There might be 8 balls here. Okay. This is just scrubbing on the loop, the bounds of the loop, right? So, and you can do that live too. So it's kind of cool. Which ball am I viewing? I'm viewing the purple one, this one right here. But what if I want to view the other one, or the other one, or the other one, or the other one, or this brown ball down here, which is the last one, right? So I can scrub on the iteration variable to scrub through space. So I can scrub on tick to scrub through time. And I can scrub on I to scrub through the space. And I'm hitting the top of the screen. But that's OK. I can scrub multiple times if I don't have enough space. Or I could just hit return. All right, let's do it that way. OK. Now let's do a little bit of debugging here. Let's just kind of look at how this thing works. Let me find something interesting. OK, let's go with the brown one hitting the bottom of the screen. OK, now I'm going to go scrub to the brown one. Right, and now I'm going to look at the inflect call here. I'm going to do a probe, Control P. No, I didn't quite get it. Ugh. Let's do it again. Right, there we go. It's returning 1 minus 1. It's causing the bounce. So I'm going to do a Control G, go to the definition of inflect 1 down here, and I can look. OK, the x1 is returning 1, and the y component is returning minus 1. Right? I can go to Control G. Why is that happening? Because the y component is 331, and the maximum, the size of the maximum y, the size of the height of the screen is 330. So that's why it's being inflected. OK? Now we have a bounce. If I want to be really brave about it, I could actually log everything on the screen, or log all the positions. I can just type log here, P. Right? And now I see a bunch of positions here. Right? And as I click on these positions, I go to the first one, the second one, the third one. Again, this is linked to the code and linked to the execution context. So as I click on this, I go to the log command, and I also set the execution context for the entry that I'm manipulating. So it's all completely linked and navigable. OK? So let's do something else here. Let me get rid of my balls here really quick. 0. I'm going to kill that, because I'm going to just do a ball out here in real space. And I'm going to get rid of the log, because I don't know what the performance implications are of that. OK. Now we're going to make this extensible method, right? So I'm going to Control G on that. Now we're in there. And now I want to make P an argument. But P is a variable, so it will change. But the initial P, right, is not an argument. So maybe we can create a P0 here. Drag that. Of course, it changed a little bit because the holy terms changed, and the default random position value is based on the identity of the holy term token. So if that ever changes, the position changes. Now I'm going to make this an argument. So I think, if you're familiar with Brett Victor's Learnable Programming essay, I think he does a little bit of this in his essay too. Or probably that's where I got the idea. So I'm going to turn that into an arg. OK? Now position is an argument of ball. And what happens? The position that I had is transferred up here as an argument, right, which is just a holy term. But now I can click on this. And I can click on this if I set the position to 0, the time to 0. Right? Now I can click on this, and I can drag it. Right? And now we can see that as we drag it, the trajectory, all the 200 frames that are being computed in the physics simulation all update in real time, basically. OK? So now we can do the same thing with the size. So now I can actually change the size. And now I'm using, instead of scrubbing on the code side, though, I can manipulate directly. Now, what about the velocity? Now, there's no, I can build in the move command and the resize command into the draw geometry logic. But obviously, geometries don't usually have velocity, so I need to add something there. So I'm going to create a new variable called v0. I'm going to initialize, that's just going to be the initial value of the velocity, and then I'm going to scrub that into a argument. OK? But of course, I can change it up here, no problem. But I want to be able to change it over here in the diagram. So what we're going to do, I'm going to save this just in case it crashes. I'm going to type in, we're going to do code completion on this thing, and we're going to call drawVec. And what drawVec does is it draws vectors, but of course it needs commands. So we're going to draw the velocity vector. And we have to specify the center of the vector, which is p. Right? Now what's kind of cool here is now when I do tick, or when I scrub on tick, I have to move my code down again so I have enough space. You can see the velocity vector that is the velocity, right? It's just drawing it out. Okay? I need more space, actually. Give me more space. All right, good. Okay? But what's cool here, let me stop coming over there, taskbar. Give me more space here. Now, this velocity here, let me make sure that we can see it, right, is a point. The point is drawn on the screen. The point can be moved, and the system will reverse engineer how that point came into being, finding a constant that it, or a Holy term that it can rewrite based on your movement. So when I move this, right, it's changing the velocity. Right? And that's not built into the system. That's just something we did ourselves. And when I stop moving it, it rewrites the velocity parameter of the ball call. Okay? So let me clamp that really quick. Minus unit. Alrighty, now let's put more balls on the screen. 1, 2, 3. All right, I put more balls on the screen, a lot. Now I'm going to select this guy here, and we see that it has a velocity vector now. Now, because this @ symbol here prepends the drawVec command, it only executes when the debug execution context of the ball method matches the ball being drawn. Okay? So as we navigate through this, we can see the vector change. So now we can change this guy and change this guy here and change this guy. And then move them around, of course, because we have our little ball editor here that allows us to do that. Okay. So now we can just do this whole simulation. We can actually do the same thing with force. Draw vec with F and P. Oh, let's make that red. Make that blue. Okay. Now I can modify the force. But actually what happens here is if I do modify this force, you see they're all changing. And why is that? Because force isn't an argument. Force is just something that's embedded in the definition of ball. Now, I could go ahead and make a force argument, promote it to an argument of ball, and it would work as you would expect. It would be an argument of ball, and then every time I modified this, I wouldn't be modifying this up here. I would be modifying something up here. Okay? All right. So if we run this now, Control R, so we see that the balls are kind of running. They have the same force acting on them, but they have different initial velocities and stuff. And then if I click on this, it will give me the last 200 frames, from 536 to 736, and I can scrub through those. But I can't scrub through the initial ones because time travel is expensive, and you need to checkpoint, and you don't want to record forever. Okay. So let me save that off, and let's restart it. So let's do another example here. Is that me? Anyways, OK. So now we're just going to draw some stuff on the screen. And so what I'm going to do is I'm going to click on the screen up here. So the little mouse is here, and if I Control-click, I will draw something on the screen, and it will just be a rectangle. So I click, I draw a rectangle. Let me make that a little bit bigger, right? And then I can scrub that into a circle. I can move that to the corner of the thing, and I can resize it to, let's say, 60. Right? And then I can do another one. This one I want to actually be a rectangle, so that's fine. 30. And then position that to some size. OK. And then another one here. And what I'm doing is I'm building a composite shape. So I want that to be a circle also. positioned at 120 and 60 radius. OK. So now I put 3 shapes on the screen, and I've placed them, and I positioned them. They all have different colors because holy terms or whatever. But what we can do is we can actually select this, and then I can control-click on this shape, and it will do a union. Right? And all it does is it moves the code around a little bit and makes a union call. Right? And we can do a union call here, too. Right? So now I have this pill shape. Right? And now we want to abstract that. So I don't know if you're familiar with Brett Victor's create by abstracting. So this is kind of an example of that. Right? And he also used a shape, too. So I'm not being incredibly original here, but I thought it was a cool demo anyways. So I'm going to create this SZ0 to act as the size of the pill. And I'm just going to connect that here to this 120/60, because that seems to be repeated a lot in this shape. So as I do that, so the tuple moves up, and the reference to the variable, the value, moves down. Right? And we can do the same thing here. I can drag the tuple components on all of the numeric references. And I can also drag it on this one, too, because it's 30, and 60 is kind of like 30, but a little bit greater. And now let's see if it works. I can make it bigger. No, it's not exactly right. So, well, so we just go ahead and scrub the minus sign. Again, I think this is part of Brett Victor's demo, too, so not an original, but it's kind of cool to explore this idea. So we have to do divide by 2, right? And now it works. OK, so now we have a pill, and it moves. Now I got to make it a reasonable size, though. 50, 50, 50. I really should have implemented snap here, but I didn't. Snap, snap, snap. OK, there you go. All right. So now we have a pill, right? And now we need to make this, now we need to create an abstraction here. So I'm going to create a def pill return holy. OK. And now I'm going to drag this, connect it to the last union. And OK, we get a call to pill, and we get an implementation of the pill method, right? And the first thing we need is a position. So if I do that, whoa, that's not useful. Let me, there we go. OK, give me the keyboard back. So I'm going to call translate via co-completion. It's going to be in some weird location. Let's give it a non-weird location here. Right, and then all I have to do is create the p variable up here, give it a holy term, connect it to the translate position, and then make that a variable, or make it an argument, sorry. Right now, if I click on this, I can move it around, and the p value here gets modified, not a global one. And then I think we need size, but the size is wrong, so we need to correct the size a bit. So it's probably 50 plus 90, so the x is 140, and this is 50. Right, because you have to add in the circle widths, too. So then we drag that down here, and now we have the size, and we make that a arg. Right, and then it appears down here. But I'm not getting the scrubbing behavior anymore, right? I can scrub here. I can scrub here, but I can't scrub the tuple, and I don't see the little dot that allows me to resize in the editor. And the problem is that there's just not enough type information. This is like an A-tup. It's not a length 2 that allows you to do the scrubbing, right? So this is using some kind of backward type inference algorithm, and sometimes you don't use SZ enough. I use SZ0 fine. It's a length 2. That could be scrubbed if it was the thing I was scrubbing, because it's used here. But SZ is just used to create SZ0. So I have to actually add an annotation in here. OK, so I add an annotation. Now I can do it. Now I can resize with a type annotation. And the final thing I need to do is add a rotation to make it a real shape. Let's just rotate, and whoa. All right. I knew that might happen. It's happened before. It just doesn't happen all the time. OK. So I will now restart my demo and start over again. No, I have it loaded up somewhere here, demo 2. All right. We'll ignore this. Make this go away. You go away. You go away. And you go away. All right. So let me go ahead and add the pill. So now I have a pill shape here, right, with position, size, and radius, right? And all the shapes that I had otherwise also had those things. Let me make this bigger. Oh, no, I could actually maximize this, can't I? All right, that's good. Right, now I'm going to create a shape on the screen again, as I started out of the demo. Draw, right, and then I'm going to make it a circle. Right, now, what's interesting here is that, and then I can move this up. Right, and I can now that when I scrub the shape, it's here, because it has the right method signature: size, position, size, and radius. So now that I put it there, I can give it a size. We can make another one. Let's see if I can just hit fill directly here. Right, do the same thing. Oh, that's right. I could also hit the screen too. Okay. And I could make this brown. And then make this the button color up here. That is not really good color correction here. Let's make that different. Right, and now we have like a, well, I guess this is a hamburger sculpture. Not as impressive as Toby's demos, I think, but I mean, this is just coming from a different direction. Okay, so that concludes my demo. How much time do I have?
4 more hours.
4 more hours.
10 minutes.
10 minutes. So, you know, I could, let me just finish up my talk here. Let's, yeah. No, I had a feature recap, but I don't think, you know, maybe if you want to pursue the slides offline, that's good. But I had the pre-skip built in here. So a lot of technology went into this demo, and I'm not really talking about technology today. I'm talking about, you know, sort of the live programming experience. But of course, to do this, right, we needed a virtual time machine. I used to call this glitch, and I think it sounds better as virtual time machine. It's like React for compilers. So if React doesn't have state, and you know, that's why React allows you to do this, like, turn your retain mode DOM into an immediate mode thing, right? And we just add back the state. And that gives us the ability to write these complex environments, but also gives us a programming model for the language I just demonstrated. And we also have this thing I call a typeless type system, which has subtyping and generics. I didn't really show that today. But it has full client-side type inference. So it will always infer the type, and it will never ask you for an annotation unless you want special scrubbing features. OK? And you know, I showed off this environment, APX. It's a custom language and environment with enhanced typography. And we use the DLR for dynamic code generation, which gives us a little bit of performance. So it's all native code at some point, but with a highly embellished runtime system. OK, so I'm going to conclude the talk. I want to conclude this here with the obvious question, which is like, and I think this question was asked at Brett Victor's 2012 Strange Loop talk. And it says, what about if I'm writing a compiler? What should my editor do then? The idea being that, you know, this kind of stuff looks cool when we're doing 2D shapes, right? But, you know, we don't really know how to scale it yet. And I think Brett's answer was telling, and I think it's worth repeating here, is that these are just design requirements for a good environment. How do we change programming to fit? And that's what I'm working on. So thanks, and I can take questions now.